Oh my god. Okay. Good morning. Do we have people in the chat today? How's everybody feeling? Say hi if you're in the chat. Welcome to our first lecture of Chem 104. Just giving everyone a minute or so. Seeing if anyone is in the chat. How's everyone doing? I hope everyone had a good break. All right, so let's get started and just kind of do an introduction of the course. So my name is Marissa Shepard, and you hopefully got an email from me. So this is live and public on YouTube, so I won't give my email over, but you should have gotten an email from me and know how to contact me. And so, like I said, email is the best way. And so there's a problem this morning with the welcome assignment. It's not showing, but I will get that showing ASAP. I think I know what the issue is. Fix that. All right, so it should be available. Yes, so that should be available. So let's look at Blackboard together. And let me, put it on student view. So you have our welcome to Chem 104. And so I just use the one shell for everything. I do not use the other Blackboard shells. So everything for lab, lecture, and recitation is in here. And on that note, make sure you are signed up for a lab, lecture, and recitation class. And then so if we go welcome to Chem 104, there's a link to the syllabus. So you can look at that at your leisure. And so everything is there. And of course, most importantly is your assignment. So everything is laid out with the due dates, but how it goes, it's pretty regular. You know, we'll start our materials. So this week we're covering just chapter 1. And then we'll have the lab open as well. So you can look at the lab this first week. That welcome assignment is due by Wednesday. So that's just so I know you're active in the class. And then next Monday, so normally assignments are due on the Monday, since that's when our class kind of starts. But if you notice, next Monday is a holiday, so I just moved that to Tuesday. And so your homework will be due and your quiz will be due, and those are all online. And that's pretty much how the week goes. You can see everything pretty much follows along. Your exam week is week 5, so that just means you have a whole week to take the exam. So the exam is due at February 12th. And then we'll just continue on. And again, we'll be kind of covering the first 9 chapters of that book. And so if you are still trying to get your textbook, I put a few chapters here. So chapters 1 through 4. And then the other thing I recommend to students, if either you don't want to spend, the money, and well, I used to say if you're not continuing on in the courses, but they haven't been running the Chem 105 and 106 courses as much. So if you're interested in them, you could always, of course, put pressure. But this is a good resource, this OpenStax textbook. I'll post a link in the chat. And so obviously it's not going to match perfectly, but all the information is in there, just basics of chemistry, essential ideas. So that's kind of what we're starting on as well. What is matter and atoms? And so everything is in there, but you might have to hunt around for different orders. So you could use this textbook as well if you're looking for a free resource. And so I'll open up the other week. So I'll try to get week 2 open for those that like to work ahead. But everything is there. So your assignments should be laid out. So homework, quiz, lab report. The labs are, again, you just kind of do on your own. You watch these videos. And if you have any, problems or questions, just ask. So, now is a good time when we're talking, when we're live, so we can go over any questions you have over the lab. Because I'm sure if you have a question, other people have a question too. And so the lab folder here just has more information about the lab. So the PDF version, and then the Word document that you can put your answers in, and then another link to the video. Oops, sorry. And then the recitation folder. And so again, make sure you signed up for the recitation section because it's part of the Chem 105 package, but it's not really any work or anything. All it is like extra time. And so in our recitation folder, there's just a copy of the answers. So of course, please attempt the homework on your own. And so on that note, right, the homework that you'll turn in, I graded just for completion. So it's kind of on you to, go through the homework, go through the answers. Do you understand? And then ask me for help. So I'm available for you. So, again, I kind of have the set time live, and we can move this around also if this doesn't work for a lot of people. So we should have 48 people in this class. And, if a lot of people say, hey, evening would be better, I'm open to moving it around. I'm here for y'all though. And even if we don't move it around, email me, make an appointment. We can set up a Zoom appointment. We can meet in person as well. So whatever we need to do, I'm flexible. I'm here for you because this is about you and your success. That's most important. All right, I think that kind of goes over the basics. Oh, and then the other thing, so before we dive into lecture here, so we have lecture. And so I have the old notes still here from another instructor, kind of different layout. And you may like that. You may like her style better. So that's available. But I will also post, so let's go back. So under this lecture 1, I post my notes that I'm going to be working off of. And so either in the PDF form or as a OneNote form. And so I like to use OneNote. And so I'll switch over to my OneNote template so you could have these same notes as well if you're interested. And again, they're available in PDF. All right, so let's go ahead and kind of start with chapter 1. And again, just ask questions in the chat just like you would in a live lecture. And, hopefully people will watch this asynchronously as well. And again, just ask questions. That's the most important thing in chemistry and learning, is just being able to have a dialogue. So that's what truly helps solidify your understanding. All right, so let's look at kind of chapter one. And so, what is chemistry? And so, if you're in the chat, feel free to jump in and throw in some ideas, right? What is chemistry? How does it relate to you? And so, that's really important. And of course, I'm kind of biased, so I like chemistry. So, I think of chemistry as a central science in a lot of ways. But we can see how it's related to a variety of different fields. So, of course, we could go into energy and nuclear chemistry. Of course, that's related to physics. Or if you were interested in like material production, we have nanotechnology, or even, right, they're trying to make all these different quantum dots that have different structures. So, of course, if you get on the nanoscale, their properties change. So that's really cool. And of course, that also would be related to material science and engineering, thinking of like how NASA has to engineer special materials to make the shuttles, right? Because they have to be really heat resistant. But all that's related to chemistry. And so you can also think about, your careers. If you want to be a nurse, potentially, of course, that's related to biology. And nurses have to understand units and how to give dosages. Sometimes you have to scale that depending on your patient size, right? A child versus an adult. So, of course, chemistry and units are important. And so, again, right, that's related to medicine. And of course, medicine, this is where I always start putting a bunch of dollar signs. And so I like to say a lot of my friends are then in, right, medicine, pharma, drug development. Obviously, that's a huge moneymaker, big industry for chemists. And again, helps with our medicine. So whatever you're into. And medicine and drugs all kind of also go into toxicology. And of course, chemistry always ends up being drug the class, as we'll talk about drugs invariably. And this is also related to food science. So, of course, this could go into metabolism if you're interested in biochemistry and understanding that better. Or just, how do we make foods? What is foods? How are they nutritious? Artificial foods, if you're into that, or kind of those synthetic meats. So that could all be food science. I mean, there's a huge, huge umbrella. And then, of course, agriculture. I'm going to put a big, more dollar signs around big ag. So that's anywhere from pesticide development and, of course, fertilizer. So fertilizer is super important. And with that, so you'll also learn in this class, I like to talk about the Haber-Bosch process. So fertilizer is usually made by H2 plus nitrogen, gives you ammonia. So ammonia is super relevant. So that's really important. This is my unbalanced reaction. Go ahead and balance it. And of course, this is a really important industrial process. It takes up a lot of energy, but obviously, right, it's also really essential to make food and feed the world. And then, of course, just taking us around, chemistry is obviously related to geochemistry and kind of what atoms comprise, the minerals, what structures are they, and then kind of the impurities that give gemstones their color. You could also go into radioactive dating, which I think we'll touch on maybe very briefly, at least half-lives and that. And of course, right, that would be related to geology. That's how you at least try to date things and get some understanding. Again, just any other thoughts on that? And so we also can say that chemistry is a study of matter. And so matter, right, is anything that has mass and takes up space. So don't forget the air that we breathe. So of course, the air was pretty nebulous for chemists for a while. And then this class will also look at chemical changes, right? How our substances, of course, converted from one to the other. So we'll learn the conservation of matter. So, right, we're not losing atoms, they just become different things. And you could think of propane burning. So most people like to think of burning for an example. And we'll also look at physical changes. And most people are familiar with physical changes. So we've all probably seen water go from ice to liquid to, of course, boiling as steam. And so we might be familiar with this already, but let's do a recap so we're all on the same page. And again, questions are always welcome. And so matter can be classified according to its state. And we're just going to focus on the three main states. So we're not really going to talk about plasma. I know people always get excited about plasma. We're just focusing on solid, liquid, and gas. And so let's take a closer look at the molecular level here. And so if we look at a solid, and we can think about ice, and so we have our solid, so particles are tightly packed and fixed in space here. And so, right, they can't really move. But we also want to think, there's still vibrational movement. So that's really important to remember. So even though we say they're solid, right, they're still vibrating. They can still vibrate, and we still have our electrons circling around. So they're still moving. So there still is movement, right? But they can't slide past one another. So that's the distinction. And sometimes we add to this. So add fixed volume, fixed shape. And so if we look now to liquid. And so liquid right now we're adding more energy. And so now they're still packed together. So they're still close, but now they can move. And so that's the distinction. So now I'll add to this. So we still have a fixed volume, but then no shape. And we've all seen that, right? So of course I have my bubbly water here, and this of course can be transferred to another container. Y'all have done that with other liquids as well, your coffee or soda, just water pouring it around. You're familiar with that. And now if we look at gases, so now they have even more energy. So now they're floating around. And so they're kind of further and further apart. And so now we can say we have no fixed volume or shape, right? So gases just conform to the shape of whatever container they're in. And of course, we also can call this property compressible. Oops, that's a bad C. Compressible. Also, I can't spell. If I ever misspell things, just help me. Oops. No, I need to hit the sidebar. So compressible. And again, you may be familiar with that. So now they put liquid nitrogen in a lot of those tires, like your tires now for your cars. And so, right, liquid nitrogen. And so it comes in those huge dewars. And then, right, so it's basically a gas that's compressed all the way down to a liquid form. And then, of course, the regulator has it come out at a high pressure. And then that causes it to come out as a gas. And, of course, expands to fill your tire. any questions about that? And so here's just a more detailed text recap of what we just looked at. So again, the solid, fixed volume, fixed shape, and we can name some examples. I'm sure y'all can name examples. So if you want to put any in the chat, feel free. So they give ice, aluminum, and diamond, of course, are solids. Gold, we could list. Liquid. So, of course, liquid we said was fixed volume, not a fixed shape. And it just gives some examples. So, water, alcohol. So, it doesn't specify which alcohol, but it could be isopropyl alcohol or isopropanol. So, that would be rubbing alcohol. That could be ethanol, which is the one that some people like to consume. Gasoline. So, that would be octane. So, all these are liquids at room temperature. Of course, you could name other substances. And then gas. Again, we mentioned they have a lot of space between them, so they are free to move. And again, we'll go into this in more detail once we cover gases, but we basically kind of assume there's no interaction between these gas molecules. And again, that's what makes them compressible, just the large amount of space between them. All right, so now we have to kind of classify matter. And well, let's think about what does this mean? And so it says that matter can be classified according to its composition. And so let's look at all these terms. So we have elements, we have compounds, and mixtures. And so now let's dive into what those are specifically. And so now it's saying, so first we have to determine, is it one type of particle? And so basically, are we asking, is it either an element or a compound? And so both of these would be a pure substance, the elements or compounds, or is it a mixture? So of course, let's define a couple of things. So a mixture then is, of course, a mix of two or more elements or compounds. And so now we have to look, we'll go back to mixture in a second. So let's look at our pure substances. So what is an element then? And so let's look at an element. And it tries to give us a hint. And so it says, is it a pure substance that is separable into simple substances? And so an element, I can find my periodic table, is just something in its pure form. So it's only made up of one type of element or one type of atom. And so your other big hint is that it's found on the periodic table. So all your elements are on the periodic table. And so if you ever had a question, right, you just double check it on the periodic table. So we have, for instance, so zinc, you can tell that is an element. What else are you guys familiar with? So carbon, perhaps. I don't know if any of y'all are eating those black ice cream cones that are the trend. See what else. Where's gold? So we have silver, we have gold, right? So all those are elements. And so just be careful about, things that people talk about. So, right, we have sodium. And so we'll learn, right? So sodium is a metal. But then sometimes, right, if people talk about sodium intake in their diet, you're not eating pure sodium, but rather probably a salt like sodium chloride, which we'll learn how to name those as we go on in our course. also have, let's just look at other elements. So iodine, that's used as a disinfectant. And so, right, the key again that it said was it can't be broken down. And so all these, right, can't be broken down. So they're only made up of one type of element. So we can add that to element. And so let's look at some other examples of elements for clarification. Oh, I forgot this one's cool. So we can do crazy colors. So only one type of atom. Maybe that's too crazy. And so what I mean by that is we can have other examples of elements. And so they're called allotropes. And so let's look at some allotropes. And so I don't really recommend Wikipedia for like history or current events, but it does a pretty decent job with science. And so I like Wikipedia for this class sometimes. It has nice pictures. So let's look at allotropes of carbon, for instance. And so if we look at this, so all an allotrope is different geometrical arrangements of the same atom. And so, right, that's the key thing with these allotropes is we said, hey, they all have to be the same atom. So what we're looking at right now is different allotropes of carbon. So again, all these are just made up of carbon. So every little point is a carbon, or every little intersection here is a carbon. And so these are all different geometrical arrangements. And you may be familiar with some of them. And so I know some people are at least familiar with diamonds. I don't know how many people have diamonds, especially, there's ethical concerns unless you get them synthetically made. So diamond is known as, of course, a very strong form. And what gives it its clarity and also, right, its strength is this repeating tetrahedral pattern. So this is shown in A up here. And then if we compare that, and right, so this is always kind of fascinating to me, is you have a diamond, which is worth so much. And then we write with another allotrope of carbon, so graphite. And so, of course, that is the pencil lead, as we call it. And so if you look at the structure, so graphite is in those sheets, right? And so that's how it's able to shear off, and how you're able to write with it is it just shears off. So they have pretty weak intermolecular forces between them. And so that allows you to write. And so I'll skip C. So this is just another structure kind of found in meteorites, but might not be as familiar with this. So this is another important one. So the C60. So this, I think, won the Nobel Prize in Chemistry a couple of years back. So this kind of led to the whole field of carbon nanotubes. So this was a huge discovery. And this is just like a soccer ball, this structure. So you can kind of see the soccer ball like structure. So C60, or the buckyball, is another allotrope. And of course, there are other ones here that have been made. Amorphous carbon. And then I'll just skip over to H. Again, another significant one. So kind of D led to H, where they started growing nanotubes in these long structures, which of course has led to a bunch of new materials and a whole large research area. And it mentions that there are, of course, other ones. So let's look at other elements. There we go. So let me put that in our notes before we forget. So allotropes, so we had carbon. So again, I would write down diamond, graphite, have some examples. The 60 carbon nanotubes. And so let's look at other ones. And so I'm just giving you, this is not an extensive list. I'm just trying to give a few of the common ones that have allotropes and some that you might be familiar with. So if we look at phosphorus here, so phosphorus, you might be familiar with white phosphorus. So that was, unfortunately used in war. And so if we scroll down, you can at least kind of appreciate that they have different structures. So here's, oh, that's P4. Where are my allotropes here? Let me search allotropes. There we go. We want the page. Sorry, that was too much information. So we have white phosphorus. So again, just appreciate this structure. So this is kind of unstable, hence why it's used. So it's highly flammable and pyrophoric, which means it ignites on contact with air. And so if we look at other forms of it, so red phosphorus is made from white phosphorus. And so it is more stable, but still not as stable as apparently black phosphorus. And then there's also violet phosphorus. So again, just different geometrical arrangements. And so this is black phosphorus. So if you read here, so thermodynamically stable. So this is the most lowest in energy. That's what it means by thermodynamically favorable. And so this is the most favorable form, again, energetically. That was phosphorus. Oh, lost my pen. And so sometimes you see phosphorus written as P4. And so again, even though it's an element, right, don't let that trick you. It's still an element. And so we'll look at one more. Apparently I have to put allotrope or something. Oh, there we go. And so the other one that you may see in chemistry is sulfur. And so sulfur is just S here, but sometimes you see it written as S8 in a chemical reaction. And so that's referring to this structure. And so most sulfur is actually in this weird 8-ring cycle. But again, there's different allotropes. You may see that as well. Again, just so you're aware. S8, so that's just sulfur. All right, any questions on kind of what is an element? Oh, I forgot. I know what I'm forgetting. Our diatomics. So our diatomics are also really important. And so we want to probably write them on the periodic table. Let's zoom in. Our diatomics. That's not actually helpful. And so our diatomics, what this means is these are certain elements that are always found paired because that's their most stable form. And so let's highlight them on the periodic table and then we'll also write them. So I would recommend also a couple of tips. So I would probably print out a periodic table, but if you are ever on the Medford campus or will be on the Medford campus, we can make an appointment and I could print out a cardstock periodic table. So I have like a nicer periodic table that I give to my in-person students. If you want to swing by in person and get a cardstock copy or, just say hi, more than happy to do that. Or we don't have to meet online just because we're an online class. You can always have in-person office hours. And so let's highlight them. So we have hydrogen. And so it's the only one that's kind of by itself. And then the rest make this pattern. They make like a little 7. Oops. I got a little wild there. And so our other ones are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So there are 7 of them. So let's rewrite them. So hydrogen, chlorine, fluorine, bromine, iodine, nitrogen, oxygen. 1, 2, 3, 4, 5, 6, 7. Okay, making sure I got them all. All right. Any questions? All right, so now let's look at a compound. So what is a compound? And so if you're in the chat, you can answer what is a compound. If you know, you can look at, you can also name some compounds if you're in the chat. And so compounds, usually the best definition is a defined chemical formula. And so with that, right, I'll give H2O, so that's water, of course, CO2, carbon dioxide. We could also list other things. And so this is where things start to get interesting. Oh my gosh. Sorry, trying to pull up stuff. And so for instance, aspirin itself, so aspirin should just refer to this compound, acetylsalic acid. So this is aspirin. But if you're referring to a specific medicine, so you want to double check the medicine, because some of them might actually be mixtures, right, of like aspirin and something else. Or, of course, I should have thought about this beforehand. Like I think Alka-Seltzer is one of the ones that has, yeah, aspirin or Alka-Seltzer, for instance. Let me pull up this page. So Alka-Seltzer would be a mixture, since this has 3 ingredients. So it has aspirin in there, but it also has the sodium bicarbonate and the citric acid. So if you guys remember, right, Alka-Seltzer is those little tablets and you put them in water, right, and they start fizzing and stuff. And so it's not just pure aspirin. So it has to have, and we'll go into this, throughout the course, but basically it has a base and it has an acid. So this is all solid. So citric acid is a solid. Sodium bicarbonate is a solid. Aspirin's a solid. So it's just that solid powder. And then, of course, in water, that gives it a medium for that reaction. But then again, right, this makes Alka-Seltzer a mixture as opposed to a pure chemical compound. So that can always be tricky when we're identifying stuff. So just kind of be aware. And on an exam, I'm not going to try to trick you. So if it ever comes up with something where you're like a little confused, you can always offer an explanation, or send me an email if you can't do it on the test. And of course, I'm open, I'm understanding. And so now let's figure out, well, where do we put Alka-Seltzer? if we're trying to classify it. So it says mixture, and we have two options, and it says, right, is it uniform throughout? So let's look at kind of what does that mean? And so uniform throughout, right, would be, does it have the same composition? Is it well mixed? And I like to think about it in terms of food, of course. So I always think, like, is the first bite the same as the last bite? And so if it is uniform, then that would be homogeneous. And so that's where I would put our Alka-Seltzer tablet. So likely it's well mixed. There's no reason why it shouldn't be homogeneous. So Alka-Seltzer. And so it's our mixed. And so let's think of heterogeneous examples. And again, I like to think of food always relatable. So we could do Rocky Road ice cream. And so, right, that makes sense why that's not uniform or heterogeneous. And so Rocky Road, right, one bite has a bunch of marshmallows, and then the next bite you eat almonds or whatever nut is in there, walnut, and maybe your next bite is all just smooth ice cream. Again, also, I'll put another example. So Java chip, Frappuccino. Right, more food here. Another good heterogeneous example is salad dressing, especially like the Italian one. Oh, I should have had it Italian. And so if you can recall what an Italian dressing looks like, it kind of separates and has that oil water mixture, and you got to shake it. And so something that's separating into its layers, right, that would definitely be heterogeneous. And so they also give the example of like wet sand. And so you can think about that, right? You get a sandy or even like a pond water sample, and it might have sediments at the bottom, and then it's kind of clear on top. So that would be heterogeneous versus, so they gave a T, but I'll put under here, switch colors again. So like a soda, like a Coca-Cola or Gatorade. Trying to think of other homogeneous mixtures. We could put on there like cheese, as long as it's, sorry, I had to sneeze. As long as it's not like a jalapeno cheese, we could let's put like jalapeno cheese right under heterogeneous. Jalapeno cheese. All right, so hopefully that kind of gives you an idea. And if you have more questions, again, always just ask. All right, and then this is just more words for your enjoyment. Kind of skip over that. We kind of went over that. And so now here's, where this is going. What are we thinking of? And so I like to make the joke that, right, a lot of chemistry is dissolving stuff in one solvent and then either evaporating it off or distilling it off and, doing it again, basically. I did a lot of dissolving, filtering, and pumping in my life as a chemist. And so one of the common techniques for separation is called a distillation. So this is a very simple distillation. And really, I should change this graphic, but maybe I just keep it to make a safety note. So I don't know why they have an open flame here. But that's a safety hazard. So I don't think people do distillations with open flames anymore. So now we have heating mantles that are, nice and safe. And there are these nice like foil things. I should just pull up a picture instead of trying to describe it. But yeah, basically they conform to the shape of the flask, and a lot of them you can set to a specific temperature, so they're quite nice. But essentially, you have heat. So, right, you just want to add heat, and you'd want to do it, you go slowly. And so, hopefully, you get off your low boiling stuff first. So, right, it boils up, and then you have this water jacket here to cool it. So, the vapors go up, then they get condensed back down. And so, this little tube, right, it's like a jacketed tube. So, you have your inner tube, it's surrounded by water. So, this stays completely dry. And then your clean compound hopefully comes out, and you uh, get it as your distillate here. And so this is used a lot. So you can even do this right under like air free conditions. And this is a really simple one. Uh, so in like the fossil fuel industry, they use like a giant, essentially, chamber to separate it out. And so you can essentially separate like complicated boiling mixtures. So this is a fractional distillation. And so they usually have some sort of levels at each one of these towers. So it's like a huge refinery tower. And so at the very top go the lowest boiling things like your butane and propane. And then down at the bottom, you have your diesel and your fuel. It's pretty cool. All right. So now we'll kind of start to get into units. And so I have to admit, right, this is where people do not like chemistry, is all the little math. So just practice, right? Keep with it. Ask me for help. Again, I'm more than happy to go through individual Zoom sessions or in person, whatever you need. So just let me know. And so let's look at, well, why do units matter so much? Why does it matter that we label things? Why does it matter that we know how to convert, that we understand units? Again, you're nurses, you have people's lives in your hands, so it's important to understand your units. And so we have this scenario. So this was 1998. We had this Boeing Delta launch vehicle. And so it lifted off. And then what we see here is, so there was a problem. Well, they didn't know it at the time. So the software that was controlling the thrusters uh, was using pounds of force. And then the second piece of code assumed that it was in the metric unit. And right, so this was a difference in engineering. So the propulsion engineers at Lockheed Martin were using force, but it standard to use metric units. So then the engineers at NASA assumed the conversion had been made, and they went along with it. And so what happened then with this unit mishap is that the spacecraft entered too close to the planet's atmosphere, and so it just burned and broke into a lot of pieces. So of course, right, that was not sure how many millions or billions of dollars lost because of a unit error. And of course, right, we won't have that much on the line in our class, but that is why it's important to put units on things, to label things, so I know what unit you're in. And so let's also talk about, how do scientists work with all these units too? Because scientists, right, are all varied in their field. So we could be looking at things really small, really large. And does anyone know what a human hair size is, at least roughly? So human hair is usually 1 times 10 to the negative 6 meters or 1 micrometer. So that's pretty thin. And then if we look at the size of an atom, does anybody know what scale? There's also a special unit for chemistry. So the size of an atom is about 1 times 10 to the negative 9 meters or 1 nanometer. Or we can also use, yes, I see in the chat, nanometers. We also have the special unit in chemistry called angstroms, which translates to 1 times 10 to the negative 10 meters. You might see that. What about an elephant? How big is an elephant? In like tons or kilograms? Any guesses? So it depends what unit you're in. Usually people say like, 2 tons to apparently maybe even 7 tons on the way larger size. And so that could be right on the order of like thousands of kilograms. So I'll just put, roughly 5,000 kilograms. So a range of there. And then anybody know the distance, the nearest star? You might know it in light years. But yeah, so it's about, so chat says 4 light years. I think I wrote down like 4.35 roughly. So yeah, about like 4 light years. And excellent with the unit, right? So that's crazy to think about, light years. So how much light can travel in a year? That's really far away. And I'll give it to you in kilometers because I definitely don't expect anyone to know that. But that would come out to 4.11 times 10 to the 13 kilometers. So that's kind of crazy to think about. And so kind of looking at this, right, taking it all in. So we're looking at things really small, really large, all over the place. It kind of depends on your discipline, of course. And so this is where we get into our metric units. And so we have, right, each measurement has a base unit. So these are just the common base units. So we'll get into moles. So this is, right, our special unit for chemistry. But you're probably familiar with meters. So that's measuring length, grams. So that's our standard unit for mass, liters for volume. And then we'll have Celsius, but we should also put under there Kelvin, which Kelvin will be really important in our gas laws chapter and thermodynamics, but we don't really touch on too much thermo. And then time, so seconds. And we don't really discuss information in here, at least not in the form of bytes, but that would be kind of the standard unit. And so multiples of 10 are, of course, created by adding a prefix to each base unit. And so that is convenient. And so it kind of depends how you want to look at it. So I think this is kind of confusing to me. So we have, this is quantity in one base unit. but I actually like, so let's go to the next page. So I think this sheet will be more useful. And so this is multiplier. And to me, this makes more sense, but this is by the base. So just note that, right? They're saying opposite things. So don't let that confuse you. So what we need to practice then is writing our conversion factors. And so what are conversion factors? So let's look at this. And we want to start off on the right foot, because if you get confused early, then that makes the class hard. So again, ask questions. And so all a conversion factor is essentially, right, a relationship. So we could write, for example, instead of looking at these metric units, what if we write a conversion factor? So we could say there are 12 inches and 1 foot. But we could also write it the other way, right? Because this is just a relationship. So what I mean by that, we could put 1 foot on top and 12 inches on bottom. So kind of, that's what we mean by conversion factors. So in this case, we're writing our relationship. So it says we have 10,000, or not 10,000, 1,000 millimeters in 1 meter. And so we're just writing it. So either 1,000 millimeters are in 1 meter, or 1 meter are in 1,000 millimeters. Except there's actually kind of 4 ways to write it. And so what I mean by that, and this could get confusing. Come on. So we looked at this. And so we have, this is the one we did as the example, right? We said there were 1,000 millimeters in 1 meter. But look at what you're given. So this is, again, by the base. So let's kind of translate this into how else we could write it. But I would encourage you to use positive exponents, just because that'll be easier to enter in when you're doing math. At least that's my opinion. And so if we're doing by the base units, right, we're saying that 1 times 10 to the negative third meters then is equal to 1 millimeter. So these are, right, equivalent statements. And of course, right, we can write it the other way. So, or 1 millimeter is equal to 1 times 10 to the negative third meters. And let me write this somewhere else, just because I don't want it to get too confusing. And right, so this is just math extras, I'll call this. And so, right, this is just to help you see. So if we're writing it, so 1 times 10 to the negative third meters is equal to 1 millimeter. So we can get back to positive exponents by multiplying by 1, right? So that's going to be times 1,000. So times 1,000 on top, times 1,000 on bottom. And so that gives us 1 meter is equal to 1 times 10 to the third millimeters. So that's how we can get back these positive exponents. So if you want to write it in all 4 ways to help you, for clarity, that might be good. I'm just seeing where we are in the class time-wise. Let's see. I think we're a little ahead of schedule, though. Just looking at the syllabus. No, we're okay. We're right on time. So let's kind of make this a focus. So we want to practice writing all these conversion factors. And so I'll probably stream until 11:20 today. And so let's go through that. So I'll just start at the top. So again, this is our multiplier by the base. Oop. Now we're saying, And I just like to use meters to help me out. So 1 times 10 to the 12, because this could be any base unit. So meters is equal to 1. And so notice, right, the big T. So T is tera, so 1 terameter. I'll write it the other way, or 1 terameter is equal to 1 times 10 to the 12 meters. If you wanted to write it in negative exponents, again, you could go back to this other relationship because it says quantity in 1 base unit. So now this is saying that 1 times 10 to the negative 12 terameters is equal to 1 meter. And then, of course, we can write that reverse. Does that make sense so far? And again, if you're watching this later and it doesn't make sense, email me. Do not hesitate, or come Wednesday. So again, I'll be streaming Monday and Wednesdays. And so now let's just continue on down. So 1 times 10 to the 9th meters is equal to 1 gigameter. Of course, we can write this the other way. It doesn't matter. If we want to write it in the negative exponent, so now we're saying 1 times 10 to the negative 9 gigameters is equal to 1 meter. Or we can write that in reverse. We'll just continue. So 1 times 10 to the 6 meters then is equal to 1. And make sure for mega you use that capital M, especially that it gets confusing if I'm using meters as an example. 1 megameter, 1 times 10 to the 6 meters. Or we can write that, of course, in negative exponents. Negative, meters. Sorry, megameters. 1 meter. Write that on reverse. Continue on with kilometers. So 1 times 10 to the 3rd meters is equal to 1 kilometer. 1 kilometer is 1 times 10 to the 3rd meters. And of course, write this in negative exponent. 1 times 10 to the negative 3rd kilometers is equal to 1 meter. And of course, flip it. Any questions? And so now we're at deci. And so again, this is by the base unit. So 10 decimeters is equal to 1 meter. 1 meter is 10 decimeters. Or 1 times 10 to the negative 1 meters is 1 decimeter. So I'll just continue with centimeters. So there are 100 centimeters in a meter. Write that both ways. Or of course, by our base unit, 1 times 10 to the negative 2 meters is 1 centimeter. And is then here. Questions? We're almost done with this page. So again, not all inclusive, but I think all of what you'll see in this class, there's ATA is negative 18, which we might see, but let's just continue. So now we have 1 times 10 to the 6 micrometers are in 1 meter, or 1 meter is 1 times 10 to the 6 micrometers. We could write that in negative exponents, right? 1 times 10 to the negative 6 meters is 1 micrometer, or 1 micrometer is 1 times 10 to the negative 6 meters. Helps me to look. 1 times 10 to the 9th nanometers, is equal to 1 meter, or 1 meter is equal to 1 times 10 to the 9th nanometers. Right, write that in negative exponents. So 1 times 10 to the negative 9th meters is 1 nanometer. 1 nanometer. 1 times 10 to the negative 9 meters. And so almost done. We'll finish these. So 1 times 10 to the 12 picometers is equal to 1 meter. Flip that. And then 1 times 10 to the negative 12 meters is 1 picometer. Write that the opposite. Head's in the way. And so the other thing is I'll post these notes at the end of the week. So after the Wednesday live stream, I'll post the notes. You can have those available for your reference. So 1 meter, 1 times 10 to the 15th femtometers. And of course, 1 times 10 to the negative 15 meters is 1 femtometer, or 1 femtometer is 1 times 10 to the negative 15 meters. All right. We have all that. If you want these posted more immediately, if you're dying, if you can't read it, let me know. This is super helpful. So I think this would be a good cheat sheet, I would say. So if you're at home, you can print this out. I would. Otherwise, right, go to campus. There are resources to print there. If you need my help, right, I can print you out a copy. Whatever you need, let me know. And so this is helpful. So this would be a good reference sheet. And so just looking into the future, all my exams are open notes. So, right, that being said, you still want to prepare, but this is a good material. Like I'm going to have this as my reference sheet. And so now where are we going with all these conversion factors? And so basically, right, we can use these conversion factors. Did I have a practice here? Oh, I didn't. Let's just practice over here then. So before we get into more practice, let's start. I kind of like starting with our American units, I'll say, just to kind of warm us up. Do these galaxy colors. So we have, let's just say we have, right, 12 inches equals 1 foot. And so right now we want to convert 5.67 feet to inches. And so this is why I wrote them all flipped and in crazy ways. And so to break this down really slowly, and again, this is just to kind of make sure everybody's on the same page. And as we feel more comfortable, right, we can kind of move faster if we need to. If we need to move slower too, again, let me know. And so, right, with this relationship, I'll formally write what I'll call our conversion factors. So that just is our relationship. as a fraction. So 12 inches is equal to 1 foot, or 1 foot is equal to 12 inches. And so I wrote it either way because it depends on our problem on which direction we're going over which conversion factor. So if we're trying to go from feet to inches, that means we're going to want inches on top as our final answer and feet on bottom to kind of cancel. That means we're going to select this conversion factor. And so let's set that up mathematically. And so I like doing it this railroad track style now, since it helps us with our units. Now I'll admit, right, the only reason why I got through physics is because of unit converting. So that really helps. And so we're just trying to multiply across. So we said we are going to use this one because we want inches. And so notice the math, right? So we write this out. Let's kind of switch pens for a second. And so if we look, we have feet. So that's going to cancel out. And so now we can punch this into our calculator. And I would make sure that you have whatever calculator you want to use on your exam ready. I also have this virtual one. So, if you want a fancy TI-83 Plus, email me and I can help you get a link or a file for this little emulator. That's pretty nice. It's a free calculator. And so now I'm just going to type this in, 5.67 times 12. And so now it gives us 68.04. And so this is what the calculator spits out. So we haven't gotten there because, we just started lecture. But we would only report this to 3 sig figs because that's what we were given in our original number. And so that means I'm going to round it to 68.0 inches. And again, we'll get into all those details as we progress. And then let's do another quick example here. And so now let's just go the other way. I'll give the same number just for entertainment. So now convert 5.67 inches to feet. Again, units matter. Give everyone a second. Kind of set that up. And I'll go through it. So again, 5.67 inches, setting it up. So now we pick the other conversion factor. So, right, we want feet now. We want inches to go away. Now I can pick the other one. So 1 foot, 12 inches. And so again, right, that inches canceling is good. I have fun with these colored pens. And so now let's look at our calculator, pull this back up. And so now we're dividing, right? So 5.67 divided by 12. And so that gives us 0.4725 feet, at least what the calculator spits out. So 0.4725. And again, we'll round to 3 sig figs. That gives us 0.473 feet. Let's see, we still have, let's go for 5 more minutes at least. People hanging on. So see if we can try this one then. So 5 meters, 2 kilometers. I'll give people a minute or so to try it. So if you have the answer, feel free to put it in the chat and then let's go through it. So again, we'll set up kind of our what we know. So 5 meters. And sometimes I just like putting it over 1 so we're clear. And now we need to pick our conversion factor. I see an answer in the chat. Excellent. And so we have 1,000 meters or in 1 kilometer, or 1 kilometer is 1,000 meters. And so I will pick this one since, of course, we want kilometers. So kilometers needs to go on top. Meters cancels. And so I think the answer in the chat looks correct. And so now we need to divide so we can practice our mental math. So 5, then 1, 2, 3. Just double checking myself with the chat. So 0.005 kilometers. Excellent. Questions on that? Let's try. Oh, actually, let's try a tricky one before we go. So let's look at this one and see if you can figure it out. And we'll go over maybe 2 ways to solve it. So try this one, 60 milligrams to 1 kilogram. Why could that be tricky? So let's start going over it. And so if you're noticing, right, this isn't to a base unit. So that's what could make it tricky. And so my recommendation for most people is try to go, right, milligrams, then we can go grams because that's our base unit. Like to joke, right, that could be our safe space here. And then we can go to kilograms. And so I kind of call this our 2-step conversion. And so let's try that. And then I'll show another way. So we have, right, our 60 milligrams. And so let's go milligrams to grams. So there's 1,000 milligrams in 1 gram. And now we have to go grams to kilograms. So 1,000 grams are in 1 kilogram. And so now we can divide. So that should be, I think, 6 times 10 to the negative 4. But I screwed up some decimals. Divided by 1,000. Oops. Oh, I was off. See? So 6 times 10 to the negative 5. So this is my most recommended way, but some people are good at this. And again, if you don't see it, don't feel bad. I definitely feel more comfortable using the two-step myself. And so if you look at milligrams, some people might recognize, well, that's 10 to the negative 3 for its factor. Kilograms is 10 to the negative third. And so that means that there's 10 to the 6 difference between them. So some people can see that. You could also divide and see that. So 10 to the third divided by 10 to the negative third. So that gives you 1, 2, 3, 4, 5, 6. So just what we said, 1 times 10 to the 6. And then remember, it's always right many small units in the big unit. So be 1 times 10 to the 6 milligrams is equal to 1 kilogram. So now we could set this up really easy. So 60 milligrams. But again, if you don't see this, don't worry if this was confusing. But then this gives us the same answer of 6 times 10 to the negative fifth kilograms. All right. Any last thoughts or questions? So I do want to plug something and plug for volunteers if people are interested. And I'll probably send an announcement about this as well, just so I hit everybody. But there is a volunteer, and I'll say extra credit opportunity. If you are, again, physically around in kind of the Medford location, I'll show this here. So we have a science expo planned at RCC. It's coming up pretty quick in 2 weeks. So January 19th, it's going to be from 10 a.m. to 2 p.m. So it's on a Friday, so that shouldn't conflict with your classes. And it's going to be on the 3rd floor of HAC. So if you want to either attend or if you want to volunteer, maybe help out. And, it's kind of geared for the whole community. So bring the kids for sure. So it's for kids. And we will have, some pizza and maybe liquid nitrogen ice cream. So if you're interested in volunteering, let me know. If you just want to come, please come. And definitely spread the word if you can. I would really appreciate that. So yeah, send me an email if you want to volunteer. But otherwise, just spread the word. All right, I think that is a good ending point for today. Again, just let me know if you have questions, and I will hang around on stream for a little bit. So that's kind of my tradition as I hang around for, at least a minute or two in case people have additional questions. And so I'll try to keep to the schedule roughly. Again, let me know if this is a really bad time for a lot of people, but otherwise I'll try to do like an hour and a half lecture stream Monday and Wednesday. And yeah, I look forward to a great quarter. Thank you for those in the chat. I really appreciate it. It helps me as well. And I keep the flow going, and, it keeps me accountable, lets me know what you don't know. And yeah, I also just like hearing from y'all. All right. Thanks again. Happy first day of winter quarter. I look forward to it. And hit me up by email if you need anything. Thanks again. Officially ending.